Hey everyone, welcome back to the channel Code with AKJ. Today is day 45 of solving LeetCode Send 5 challenge, and today's problem is reorder routes to make all paths lead to the city 0. So this is a beautiful problem based on graphs and trees, and if you are new here or enjoying this series, don't forget to subscribe to the channel for daily updates and problem explanations. So let's get started with our problem. So the problem statement says there are n cities numbered from 0 to n-1 and n-1 roads such that there is only one way to travel between two different cities. So this network forms a tree. Last year, the Ministry of Transport decided to orient the roads in one direction because they are too narrow. Roads are represented by connections where connections of I is equals to A of I comma B of I. So this generally represents a road from city AI to city BI. This year there will be a big event in the capital city 0 and many people want to travel to this city. Your task consists of reorienting some roads such that each city can visit the city 0. Return the minimum number of edges changed, and it's guaranteed that each city can reach city 0 after reorder. So the problem statement says we are given n cities and n-1 directed roads in the form of connections of I, that is equals to A of I and B of I, which generally represents a road from city A to city B. And our task here is to reorient the minimum number of edges or the roads in such a way that every city can reach the city 0, which is a capital city. So let's understand these two given examples. So here I have drawn the two examples, and here our aim is to make sure that we visit this capital city 0 from any other cities, which means we should be able to visit city 0 from 2, 3, 1, 4 and 5. We need to reverse the direction of our edges, and ultimately we need to do minimum changes to these edges in order to make all the cities visit city 0. So let's try to do that. So in this given example, let's check from city 1, are we able to visit city 0 from city 1? So from city 1 we are able to move to city 3, but we are not able to move to city 0. We can say that we need to change this particular edge in order to move from city 1 to city 0. And coming to the city 3, are we able to move to city 0 from city 3? And that is no, because the direction is opposite. In order to move to city 0, we need to move to city 1 first, and then we can move to city 0. So in this way, we'll try to check from each and every city whether we are able to move to city 0. Here we can see that from city 4 we are able to reach city 0, so this particular edge is fine. And these two edges needs to be changed as they are in the opposite direction of the city 0. So overall, by looking all these edges and our aim to reach city 0, that is our capital, we need to make sure that all the edges are towards the city 0. So if all the edges are towards the capital, that is city 0, then we are able to move to the city 0 from any of the other cities. So that is our aim of this problem statement, that is to reverse all the edges and it should be towards the city 0. So in this given example, the edges which we need to change to ensure that we reach capital 0 are the edges 0 to 1 and 1 to 3 and 4 to 5. So after changing these three edges, the whole representation would be changed in this way, that is 0, so 1 pointing to 0, 3 pointing to 1, 2 pointing to 3, 4 pointing to 0 and 5 pointing to 4. So these are the three edges we have changed. So for this given example, our answer would be 3. 3 is the minimum changes of the edges in order to make sure that we visit 0 from any of the cities. So now we can check that from any of the city we can reach the capital 0. So if we choose city 3, then from city 3 we can move to city 1, and from city 1 we can move to city 0. So we are able to reach city 0 from city 3. In the same way, if we consider city 5, we are able to reach city 0 by moving to city 4 first and then 4 to 0. So in this way, for this given example, our answer would be 3. Coming to the second example, our aim here is to reverse all the edges and make all the edges pointing towards 0. So since this edge is already pointing to 0, so we don't need to reverse this particular edge. And here, if we consider this edge 1 to 2, since it is pointing in the opposite direction of 0, try to consider changing this direction. So this would be one of the changes. And coming to this particular edge, since it is pointing towards 0, so ignore this edge. And coming to the final edge, since it is in the opposite direction of the city 0, we can consider it changing. So for this given example, after changing all the edges and pointing it towards the capital 0, the graph would look like this. That is 1 pointing to 0, 2 pointing to 1, 3 pointing to 2, and 4 pointing to 3. And for this given example, our minimum changes would be 2. That is the edge from 1 to 2 and 3 to 4. So this is all about our problem statement. So let's get started with our brute force approach. So in our brute force idea, for every edge we'll try to reverse it and keep it as it is. So we'll have two options, whether to reverse it or not. And we'll check if all the nodes are able to visit the capital 0 or not. Finally, we'll count the minimum number of reversals required. So the first step in our brute force approach here is to either reverse this edge or keep it as it is. So we'll be having two options, whether to reverse it or not. So we'll first check by it as it is, and then trying to check whether all the cities are able to visit capital 0 or not. And our second option would be to try to reverse that particular edge and again check whether all the cities are able to visit this capital 0 or not. So our idea here is that for every edge we'll try to reverse the edge or we'll keep it as it is. So we'll have two options. Option 1, we'll keep it as it is, and option 2, we'll try to reverse it. So for every edge we'll try these two options, and this would be our first step. And our second step here would be to check whether all the cities are able to visit capital 0 or not. So we'll either use BFS or DFS to check whether we are able to visit capital 0 or not. And finally, we'll try to track the minimum number of reversals required for each and every option, and we'll track it by storing the value in minimum changes. And after performing these three steps, we'll get our minimum changes. We'll return minimum changes. So these are the three steps we'll be performing in our brute force approach, and we need to note that by exploring all the options, that is option 1 and option 2, we'll be generating 2 power n minus 1 edges. So we'll be generating these many combinations, so give us TLE in our time complexity, whereas in our space complexity, since we are using recursive approach, so it would use recursive stack, and the maximum value it would be storing would be O of n plus E, where n is the number of cities and E are the number of edges. So since we are using recursive approach, so the approach is exponential, and definitely it's inefficient, not practical for larger inputs. As it is a brute force approach, we'll still try to code this approach and try to submit. So let's quickly understand how our brute force approach works. So I'll just explain one or two steps and then we'll move on to our code. So here we'll try to grab each and every connections between city A and city B, and we'll try to create a graph. And since our brute force approach takes three steps, that is, first step is keep the edge as it is or try to reverse that edge. And second step would be to check whether we are able to reach city 0 from all the other cities. And finally, we'll try to track our minimum changes and return that minimum change variable. So here we'll first try to take the first connection, that is 0 to 1. We are here. Our first option is to keep the edge as it is. So we are trying to keep each and every edge initially as it is, and we'll try to increase the changes. So we have taken the first index, and again 1 to 3, the changes becomes 2. So we'll take a changes variable. So first was 1, and again it changed to 2, and 2 to 3, change updates to 3, 4 to 0, changes becomes 4, and 4 to 5, that is changes becomes 5. So now, since we have generated a graph by choosing the first option, that is keeping the edge as it is, and for 5 changes, we will now try to check whether we are able to reach the capital city 0 from all the other cities or not. So we'll use a BFS, where we'll try to use a queue, and we'll check whether we are able to visit all the other cities from 0 or not. So we can clearly see that we are not able to reach city 2 and city 4. So while trying to reverse each and every edge, we'll try to backtrack. So our last edge was 4 to 5 and we'll try to reverse this edge. So after reversing this edge, our graph becomes 0 to 1, 1 to 3, 2 to 3, 4 to 0 and 5 to 4. So after reversing this edge, we'll again check whether we are able to reach the city 0 from all the other states or not. So here we can see that again we are not able to reach city 0 from the city 2. Since we are able to reach city 0 from 5, 4, but we are not able to reach the city 0 from 1, 3 or 2. We'll try to reverse another edge and we'll try to check. So since here this edge is already pointing to 0, we'll try to keep this edge as it is. And here since we have changed this edge, we'll keep our change value 1. And now we'll try to change this particular edge. And here since the edge is already pointing towards 0, we'll try to keep it as well. And we'll try to change this edge now. So after changing this edge, graph becomes 0 to 1 and 3 to 1, 2 to 3, 4 to 0 and 5 to 4. So now again we'll check with the help of our BFS whether we are able to reach the city 0 or not. So here since we are not able to reach the city 0 from city 1, we'll again try to reverse this particular edge. So after reversing this particular edge, and now the change was initially 2 and now the change becomes 3. Our final graph would look like this, that is 1 to 0, 3 to 1, 2 to 3, 4 to 0 and 5 to 4. So in this way we are able to reach the city capital 0 from all the other cities for the main event, and our answer for this given example would be 3. So the minimum number of changes we require to make sure that we visit the capital 0 from all the other cities would be 3. So let's quickly code this brute force approach, and since we are trying to recursively check each and every edge and try to find the combination where we are able to reach the city 0, the formula would be 2 power n minus 1, which means it generates 2 power n minus 1 cases for our recursive approach. And here for this given example, since there are 6 cities, so 2 power 5, that is 32 combinations. So for these 32 combination, we are trying to create the graph and we are trying to check whether the cities are reachable to capital 0 or not. So the time complexity would be 2 power n minus 1, which is exponential, which is obviously inefficient and not practical for larger inputs. And the space complexity here would be O of n, that is for recursive stack depth. So let's quickly code this approach and let's move on to our optimal solution. So here's the code for our brute force approach, where we are trying to create the graph for each and every combination using recursive by taking two options, either keeping the direction u to v or trying to reverse the direction. So for the graph representation, here I have taken vector of vector, size n, number of trees, and here I have used DFS try function, sending the index value which would be initially 0 and size of our connections vector, graph connections vector itself, and the changes variable which would be initially 0. So our DFS function goes like this, where it will take index n and first we'll grab the u and v values with the help of our index of 0 and index of 1. And here our first option would be that keeping the direction as it is, that is u to v. And since we are keeping the directions as it is, we'll try to increase our changes plus 1 as it might need reversal at the end. So for every next index, we are trying to create a new graph, trying to add edges to the graph. And when it reaches the connections of size, we'll check whether we are able to reach the city 0 from all the other cities or not with the help of all reachable function by sending the graph and the size. And if it is reachable, we will try to compare with the changes with our minimum changes. So here minimum changes would be initially int max, which I have declared globally, and if we are able to reach for this given combination, if we are able to reach the city 0, we'll try to compare the changes value with our minimum changes and we'll update our minimum changes and we'll return from that function call. So the all reachable function goes like this, where I've used BFS function with the help of a visited array, which would be initially false, which means this particular city is not visited initially. So we'll first initially push the capital 0 and we'll mark it as true, and we'll run a loop until or unless all its neighbors are visited true. So after marking all its neighbors as true, we'll check whether any of the city is still unmarked. So if it is still unmarked, which means there is a city to which we are not able to reach city 0. So if it is unvisited, we'll return false, and if all the cities are visited, which will return true. So this would be our all reachable function, and this is our DFS try function. After finishing this particular option 1, we'll try to pop back the second option, that is the reverse direction. So after popping back, we'll try to use this line and try to reverse that direction, and again we'll check with the help of all reachable. So this is how the flow of this brute force approach works. And since the time complexity is exponential, it might give memory limit exceeded or the time limit exceeded. So let's quickly run this code. It's working on smaller cases, so let's submit. Yeah, it gave memory limit exceeded. So it almost passed half of the test cases, but still complexity was exponential. That is why we got memory limit exceeded, because of recursive stack depth. So this was the brute force approach. So let's quickly jump on to our optimal approach, where we'll try to optimize our time complexity and reduce our time complexity from exponential to linear. And also we'll try to optimize our space complexity. So let's quickly go through our optimal approach, where we will try to track the direction and we'll use DFS. So the main idea here is we'll treat each edge as AI BI, since AI and BI, that is the connection between the city A and B. And if the edge is from parent to child, that is away from 0. So here we'll consider both the cities as parent and child based on the direction. So there will be a parent city and the child city. And if the direction is from parent to child, it is moving away from the parent. So we'll have two options, that is, if the edge is from parent to child, that is away from 0, we'll need to reverse it, which is obvious, which we have already seen in our brute force approach. So since our aim here is to reorder all the edges pointing towards the city 0, as we need to move to city 0 from any of the city. So our main goal here is to reverse all the edges which are moving away from the city 0. So that is our first option, that is, if the edge is moving from parent to child, we need to reverse it. And our second option here is, if the edge is from child to parent, which is towards the 0, we don't need to reverse it. And its direction, whether it is moving away or towards the city 0, and based on that away and towards direction, we'll try to assign a value to it, and then we'll create an adjacency list storing each edge as a pair, that is neighbor and distance. We'll create an adjacency list considering each edge as a pair, that is 1 if the original direction from A to B, and 0 if the reverse direction B to A. That is the same case, that is parent or child. So if it is moving away from the parent, we'll consider it as a 1, and if it is moving towards the parent, then we'll consider 0. 1 means we need to reverse this edge, 0 means we don't need to reverse this edge. And finally we'll use a DFS traversal starting from 0, and we'll try to add the value that is stored in the distance variable in the pair. And as we move towards the other cities with the help of DFS traversal, we'll try to store its distance value, that is whether it is 1 or 0. And finally we'll sum up all the distances, that is distance plus equals to again DFS call moving to other cities, and all the sum up distance would be our reversal count. So for every outgoing original edge, that is the direction 1, we need to reverse that edge, we need to increment that count also. So this would be our optimal approach, where we are trying to track the direction, whether it is moving outwards of city 0 or moving towards the city 0. So if it is moving outwards to 0, which means we need to reverse that particular edge, and we will assign that outward edge as 1, and the edge which is coming towards 0 will assign it as 0, as we don't need to reverse that particular edge. By assigning the value to the edge, we'll be able to understand which particular edge needs to be reversed, and by adding all those outward edges, we'll be able to track the reversal edges, and finally we'll return that value. So let's quickly dry run with this given example. So for this given edge 0 to 1, the assigned value would be 1, and for again 1 to 3, the assigned value would be 1, and for 3 to 2, since the edge is moving towards the parent from the child, we'll assign it as 0. And here again, the parent is 0 and the child is 0, and the edge is moving towards the parent, we'll assign this as 0. And again here, the parent is 4 and the child is 5, and the edge is moving outwards to the parent, so we'll assign this edge as 1. And after starting a DFS node from 0, we can see that distance or the edge here is assigned value 1, so the counter would be initially 0. So here the value is 1, so the counter would be updated to 1. Again, when we moved from this city to this city, here again the distance is 1 or the assigned value is 1, so we'll update our count variable to 2. Again, when we move to this city, the value is 0, so the count remains 2. So when we move to 0 to 4, the value is assigned to 4 is 0, so the count remains 2. And when we move to 4 to 5, the assigned value is 1, so we'll update our count value from 2 to 3. So after visiting all the other cities, starting DFS from city capital 0, our count variable becomes 3, and this is the value will return as an answer. So for this given example, we have 3 edges which needs to be reversed in order to make all the city visit the city 0. So for this approach, our time complexity would be O of n, as each node and edge is visited once in DFS traversal, and the space complexity will also be O of n, as we are using a simple adjacency list and recursive stack. So in this way, we have optimized the time complexity from exponential to linear, and the space complexity, which was O of n plus e, have reduced to O of n. So this was our optimal approach. So let's quickly code this approach and submit it. So let's code our optimal approach quickly. So to create an adjacency list of pair of int comma int, so I'll use an order map of int of vector of pair of int comma int, and name as adjacency. We'll go over all the connections in connections 2D vector. We'll grab the u value which is stored in index 0 and v value stored in index 1. And now we'll assign these edges based on parent child direction. So we'll assign it as 1 if it is original direction, and we'll assign it as 0 if it is a reversed direction. So since we need the reverse direction, which is towards the capital 0, we'll assign it as 0. And if it is an original direction which is moving outwards of u, that is from u to v, then we'll assign it as 1. So after creating this adjacency list, we'll give a call to DFS, sending the current node, starting node, that is the capital city, and its parent, that is initially -1. So the parent of capital city is -1, and sending the adjacency list. And finally, we'll return our count. So let's declare our count variable globally, which would be initially 0. And let's write our DFS function. So it would take node, it would take parent and adjacency list. So we'll use a for each loop, which will have the neighbor and the direction. For this particular node's neighbor and direction, if the neighbor is the parent of the current node, we'll continue and we'll increment our count variable based on our direction, and we'll again give a DFS call sending our neighbor node. And the parent of our neighbor node would be the current node, and we'll also send our adjacency list. So let's quickly run this code. It's working, so let's submit. As you can see, this gives us successful submission, as the time complexity of this approach is O of n and the space complexity of this approach is also O of n. So if you're finding this helpful, don't forget to subscribe to the channel, like and comment on this particular video. It really motivates me to keep posting these solutions daily. So let's quickly wrap this with a quick summary. So let's move to time and space complexity analysis. So for the brute force approach, We have used a recursive and backtracking approach where we are trying to generate a graph with all the combinations which gave us 2 power n minus 1 combinations. So the time complexity of our brute force approach was O of 2 power n minus 1 and the space complexity was O of n plus e for the recursive stack. And we have optimized this time complexity from exponential to the linear in our optimal approach, where we have used the direction tracking and a simple BFS. So with the help of direction tracking, assigning each and every node based on outwards and inwards, that is outwards to 1 and inwards to 0. And whereas coming to the space complexity was O of n for the DFS recursive stack. So that's it for day 45 of LeetCode 75 challenge. We explored both the brute force and the optimized DFS solution for the reorder routes to make all paths lead to the city 0 problem. So if you like this video, give it a thumbs up, share it with your friends and subscribe to the channel for more daily problem solving explanations, and I'll see you in the next one. Thank you.